Hello, my name is Daniela Diaz Caballero, and for this video I will be discussing Physics 2212 Lab 4, Macroscopic View of DC and RC Circuits. During this video, I will give a brief introduction to the experiment, which will include the purpose of the lab, any assumptions that were made, and the results that were discovered. From there, I would also include the data and observations from the experiment, as well as my computations. Last but not least, I will conclude by discussing theoretical questions that can be inferred by our findings of the experiment. The purpose of this experiment is to predict the behavior of circuits containing resistors in series and in parallel. Use multimeters to measure the actual values of conventional current and potential differences in the circuit, and examine the behavior of occaming resistors and capacitors. To do this, we will be using the Online Circuit Construction Kit, CCK, from the Colorado FET project to explore time-dependent voltage and current in a DC circuit. The fundamental principles we covered during this lab were the principles of energy conservation, loop rule, and the current conservation. The result from this experiment was that the time constant of a system was approximately 6 seconds. Before going into the calculations for the experiment, let's discuss the pre-lab instructions and expectations. For Lab 4, we utilized the Online Circuit Construction Kit from the Colorado FET project to create a simple series circuit of two 1.5 volt batteries, two resistors, and two ammeters as shown in the image. By using the loop and node rule, we were then able to predict the readings of the ammeters and voltmeters before we even ran the simulated circuits. From there, we were able to model and predict the time constant of a system through graphing. Now, moving on to our data collected from Lab 4. For the first system, the simple series circuit, I predicted that the currents I1 and I2 would measure 0.0 ammeters by using the formula I equals volt divided by resistors. When connecting the two batteries, it shows that our predictions were right. Notice that when we reverse the connections to one of the ammeters, the ammeter reads the same result. When replacing one of the ammeters with a voltmeter, the top ammeter read 0 amps and the voltmeter read -3 volts. Continuing with the experiment, when we remove the voltmeter from the circuit, close the circuit with a wire and use the voltmeter to measure the potential difference for each part of the path around the circuit. From there, we recorded the current I, and the results are shown below. AB equals 3 volts, BC equals 0 volts, CD equals -0.959 volts, DE equals 0 volts, EF equals -2.041 volts, FG equals 0 volts, GH equals 0 volts, and HA equals 0 volts. On the right, you will find the approximate graph of potential relative to the negative end of the battery versus position around the circuits. As you can see, the slope is steeper in areas A, C, and E, since the electric field is strongest during those points. Notice that when you sum the individual potential differences, the measured differences should actually add up to 0 because it is a closed circuit. For our case, our measured differences do add up, so we know that we are on the right track. A couple of observations from our experiment is that from the results, we can calculate the resistance of each of the following circuit elements. The resistor 47 ohms equals 47.95 ohms, resistor 100 ohms equals 102.05 ohms, resistor wire equals 0 ohms, resistor ammeter equals 0 ohms. Now, moving on to our second system, the RC circuit. We investigated RC circuits to observe how a capacitor changes. We used a 10 ohms bulb, a 20 ohms bulb, one 9 volt battery, and a 200 millifarad capacitor. With this, we can see that when charging a capacitor, current flows into the capacitor, while discharging, the current flows out of the capacitor. These actions cause the light bulb to grow brightly and then dim and go out as the capacitor reaches the peak charge or empties of charge completely due to the current flows stopping after charging or discharging occurs. Here you will find the images of the RC circuit. Now we're going to transition and talk about our third system, the time-dependent voltage across the discharging capacitor, the RC circuit. So, in this system, it consisted of a 9 volt battery, a 30 ohms light bulb, and a 0.2 farad capacitor. In this case, we paused the simulation and recorded values of the voltage of the capacitor as it discharged over time. We got the values of the voltage and the time associated for a time of 20 seconds, which we used to plug into an Excel graph to use in the equation ln delta V divided by delta V initial. In this graph, you can see the time and volt measurement And you can also see how we used these values to find the time constant of the system. These values created the graph shown below, which had a slope being the negative reciprocal of our time constant that we were looking for. From this, we can calculate that the time constant for the entire system was approximately 6 seconds, which would equal our expected value of 6 seconds that we would calculate from multiplying the total resistance by the capacitance of our capacitor. Last but not least, we will be discussing some theoretical questions that we can infer based on what we learned in this experiment. The first question is, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how it would have affected the circuit you hooked it up to? If you did this lab with the real circuit components, access the virtual circuit link and see if you can determine how it behaved differently from the real ammeter you use. So a real ammeter would be less perfect and would therefore add additional resistance. The real ammeter would have their own resistance, which would then mess up their calculations and would end up reading a lower current than that of the current of the system without the ammeter. For the second question is, what if you were doing this lab in real life and used a battery to charge a real capacitor with no resistor to the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. This model predicts that the charge of the capacitor would fully charge immediately, while in real life this wouldn't happen, since the batteries have their own resistance, and therefore they would end up being a slower process. In addition, we should also consider the fact that batteries in real life can drain and that equipment can wear down, so these things would not happen in real life. Last but not least, our conclusion. Based on this experiment, we can conclude that the time constant for the entire system was approximately 6 seconds from our Excel calculations, which would equal our expected value of 6 seconds that we would calculate from multiplying the total resistance by the capacitance of our capacitor. Thank you so much for watching, and please do not hesitate to reach out if you have any questions. I will see you next time for Lab 5. Thank you.